Hello everyone, this is Totro, a freshman majoring in biomedical science and engineering at IIT Guwahati with a deep interest in the mathematics behind self-similar patterns. Today, our mission is to really get into the math that helps us understand the human body, specifically complex analysis and fractal geometry. Today, I'll be speaking on its specific applications in cancer diagnosis, along with my co-speakers, Tom, Amanda, and Sarah.
Fractal geometry is the study of shapes that exhibit self-similarity, meaning they look the same at different scales. Imagine zooming into a coastline. The smaller sections resemble the overall shape. Fractals often have dimensions that are not whole numbers. For instance, a jagged line might have a dimension between 1 and 2, indicating it's more complex than a simple line, but doesn't fill a two-dimensional space. This is because the concept of dimensions in fractals arises not from topological dimensions but from Hausdorff dimension, which we will calculate shortly.
Now the question arises, how do we find the Hausdorff dimension?
Yeah, that's an interesting question. The definition with those infimums and coverings makes my head spin.
I know. The formal definition is brutal. But for most nice fractals, the self-similar ones, there's a fantastic shortcut. Like the Sierpinski triangle? Exactly. You just need two numbers. How many copies and make up the next iteration, and the scaling factor R for each copy. Okay, so for Sierpinski, that's n equals 3 copies, each scaled by R equals 1/2.
Bingo. The dimension d is just log n divided by log 1 by r. So, log 3 by log 2. Way easier.
Well, have you heard about the Mandelbrot set? Its boundary, which is supposed to have a topological dimension of 1, has, interestingly, a Hausdorff dimension of 2. This means that despite being a curve, the boundary is so complex and detailed that it has the same fractal dimension as a 2D area, reflecting its extreme fractal nature.
Summing up, fractals, illustrated by the Mandelbrot set, defy classical Euclidean geometry by introducing fractional dimensions, like the Hausdorff-Besicovitch dimension, that better capture their complexity than traditional integer dimensions. Unlike the simple scaling of standard shapes, fractals reveal infinite, complex patterns when magnified. This property makes them essential for bridging mathematical concepts with the intricate, real-world complexity found in nature.
Now that we have learned something very basic about fractals, let us move on to our main aim, cancer detection.
Traditional mathematics often describes the world using smooth, predictable shapes. But the human body isn't like that. It's complex, irregular, and filled with intricate patterns from the branching of our blood vessels to the firing of neurons in our brain.
On top of that, cancer growth is even more complicated. The main challenge here is that cancer growth isn't neat and tidy. It's messy, uncontrolled proliferation. These mutated cells create tumors, and these tumors are highly irregular, complicated structures. Our standard Euclidean geometry, the maths of perfect circles and squares, wouldn't be able to handle this challenge.
Well, that brings us to the new breakthrough in biomedical engineering that can revolutionize the way we see cancer forever. Till now, cancer was seen by biologists as a mass of uncontrolled proliferating cells. But now, mathematicians have discovered yet another angle to this disease.
The article argues that cancer should be viewed as a systems biology disease, meaning it's a disruption of the entire tissue architecture rather than just a result of faulty genes, the reductionist view. In this context, the physical shape and structure of cells and tissues become critical indicators of the disease state. The core idea is function follows form. This is where fractal analysis comes in.
The fractal analysis approach uses fractal geometry as a quantitative method to measure the complexity and integrity of biological structures. Instead of measuring simple length or area, it calculates a value that describes how complex a shape is. According to the article, this approach is applied to 1. Tumor morphology, analyzing the shape of the tumor, particularly in the epithelia stroma interface, that is, the boundary between the cancer cells and the surrounding connective tissue. Number 2. Cellular structures, analyzing the texture and shape of the components inside the cell, like the nuclear chromatin, from the microscopic images. Number 3. Vascular networks, assessing the complex branching patterns of blood vessels, angiogenesis, as it is called, within a tumor specifically. As we know, the blood vessels become more disorganized and chaotic within a tumor. By quantifying the complexity of these structures, fractal analysis can provide reliable diagnostic and prognostic information. For example, the article cites studies showing that 1. The complexity of the tumor host boundary increases as the lesion progresses from normal to a pre-malignant to an invasive cancer. Number 2. Fractal analysis can help discriminate between benign and malignant tumors and distinguish between low and high-grade tumors. Number 3. Conversely, when the cancer cells were induced to differentiate, which is to become more normal, their measured complexity decreased. Essentially, fractal analysis provides a mathematical number to quantify the disorganization and complexity of the tissue, which the article links directly to the cancerous state.
However, fractals alone just give us a static picture. For a better analysis, we have to harness the power of complex analysis in the field of fractal geometry. Complex analysis is the calculus of functions in a complex plane. It then defines the key components of a complex number, z. Standard form, z equals x plus I, where x is a real part and y is an imaginary part. Conjugate, z equals x, I. Modulus, z equals square root x squared plus y squared. Polar form, z equals our cosine theta plus our I sine theta.
But, how does complex analysis help in our case? Complex analysis is the parent field of fractal geometry. The most famous fractals, like the Mandelbrot set, are generated using equations in the complex plane, which use complex numbers. The mathematics from complex analysis was used to develop algorithms, such as the box counting method, which are needed to measure the fractal dimension of real-world objects, including tumors. In short, complex analysis provides the foundational theory for the fractal tools that are used to measure the chaotic signature of cancer.
Let us cover the box counting algorithm in brief. The box counting method as an algorithm is used to determine an object's fractal dimension, which measures its complexity and irregularity. The method works by overlaying a grid on the shape and counting the boxes that intersect with it. It outlines a four-step process. Overlay a grid. Start with a large grid, example 2 cross 2, over the shape. Number 2. Count. Count all the boxes that contain any part of the shape. Number 3. Refine the grid. Repeat the process with increasingly finer grids, noting that the box size R gets smaller. As the box size R gets smaller, the number of boxes counted, that is N, gets larger. Number 4. Plot the data. Create a log-log graph of log n versus log 1 by r. The slope of the resulting line is the fractal dimension.
Now, let's talk about one real-world prototype that will come up very soon.
This is our prototypic plan for applying fractal geometry directly to disease detection. The entire plan is built on a key visual difference between benign and malignant tumors, which you can see in the black box. A benign tumor tends to be smooth, well-defined, and spherical. Its boundary is Euclidean. Think of a simple circle. Because it's so simple, its fractal dimension on a 2D slice is very low, around 1. A malignant tumor, on the other hand, is invasive, irregular, and spiky. It grows chaotically, and its boundary is fractal. This isn't random. The tumor is actively trying to maximize its surface area for nutrient absorption and to invade the surrounding tissue. Because of this high complexity, its fractal dimension is significantly higher, greater than 1. Typically, we see values a range of 1.2 to 1.7. This clear mathematical difference is what we want to exploit. So here's a plan. We propose designing a machine in artificial intelligence that can interpret medical images like MRIs, CT scans, and biopsy samples. This machine's core function will be to analyze the fractal dimensions of the structures it sees. By training machine learning models on large datasets, the AI will learn to identify these complex, chaotic patterns and correlate them with different cancer stages. The benefits here are threefold. It dramatically improves diagnostic accuracy. It allows for earlier detection, which is the most critical factor in successful treatment. And ultimately, it provides a user-friendly tool for doctors, representing a significant advance in personalized medicine and completely transforming how we approach cancer diagnosis.
Summing up, we have highlighted three key areas where these mathematical fields are applied in medicine. 1. Tumors. Fractal analysis is used to improve the detection of tumor morphology, which is basically its shape and structure. Number 2. Progression. Complex analysis helps in monitoring the disease progression models, which is dynamic. Number 3. Delivery, which is its ultimate application. Fractal metrics can be used to effectively optimize drug delivery methods.
I will be summarizing the main argument of the presentation before the final highlights are shared. Advanced mathematical tools, specifically fractal and complex analysis, hold immense potential for enhancing disease detection and management. As a future direction, it proposes that integrating these mathematical analyses with AI and personalized medicine can revolutionize healthcare. This integration is expected to pave the way for new advancements like real-time monitoring and ultimately lead to improved patient outcomes.
I will conclude this insightful discussion by outlining the key advantages of using fractal and complex analysis in medicine. Fractal analysis improves disease detection by uncovering hidden patterns within biological data. This allows for a more accurate diagnosis and a deeper understanding of complex biological structures. Complex analysis makes it possible to model complex biological processes. This leads to better predictions and provides new insights into disease mechanisms, which ultimately helps in developing more effective treatments.
With this, I would like to conclude by saying thank you.